Hi everyone, this is Mr. Bowman, and in this chapter of Intro Calculus, we're going to use all the rules that we learned for derivatives for applications. And the first thing we're going to start out with is we're going to start out with writing equations of lines and using those lines to estimate the value of a function. So if you remember from Algebra 2 and Pre-Calculus, maybe even Algebra 1, point-slope form for the equation of a line is y minus y1 is equal to m times x minus x1, where m is the slope and x1, y1 is a point on the line. We're going to use that idea a lot. So if we think of it, instead of y, we're going to use f of x in place of y. So f of x minus y1 is equal to m times x minus x1. And we solve for f of x, we get f of x is equal to m times x minus x1 plus y1. And basically we're going to use that idea to estimate the value of a function near the point that we find the tangent line. So here's an example. The average retail price during the 1990s of a pound of salted grade 2A butter can be modeled as P of t is equal to 5.17 t squared minus 28.7 t plus 195 cents. So you've got a quadratic there. And if we look at that quadratic graph, you see down below, with t being the years since 1990, and the blue being the actual function p of t, so this is p of t. And then there's that dotted line there, and that dotted line is our f of x from above. So what we're going to do is we are going to pick a point on both the curve and the line. That's the point of tangency there that I highlighted in red. We're going to find the value of the derivative, which gives us the slope in that f of x equation. So that'll give us m. And then we have the point of tangency, so we'll have x1 and we'll have y1. And then we'll plug that some other point in after we found the equation of that line that's near the point of tangency, and we will use that to estimate the value of the function. So you can see a little bit to the right of the point I highlighted, there's a point that has coordinates 323, and that's a point on the tangent line, but that should be very close to the value of the function if that point is close to our point of tangency. So let's add a little context to this. Find and interpret P of 8. So P of 8, if you plug in 8, is equal to 296, and you can verify that yourself. And that would be the average retail price of 1 pound of 2A butter in 1998, years after 1990, was 296 cents. Now we're going to find and interpret P prime of 8. So P prime of t, let's find that derivative first, is going to be equal to, using the power rule, the 2 comes down, 2 times 5.17 is 10.34 t minus 28.7. So P prime of 8, if you plug those values in, is equal to 54.02. So in 1998, the average price of 1 pound of to a butter was increasing at a rate of 54.02 dollars per year. Okay, so nothing we've done so far is new. Here's where the new part comes in. It says find the equation of the line tangent to P of t at t equal 8 and call it FL of x. So we're going to go up here, we're going to label that FL of x. And FL of x is equal to m times x minus x1 plus y1. Okay, so first of all, m is equal to p prime of 8 because we're finding the line at the point of tangency. P prime of 8, we're going to round off to 54 cents per year. Sorry, and I noticed I made a mistake earlier. That would be 54 cents per year in the derivative. 54 cents per year is our slope. And the point from the P of 8 is 8, 296. So FL of x is equal to 54 times x minus 8 plus 296. And that's how we find the equation of the line tangent to a curve at a given point. We know the points on the curve, 8 to 296. We know the derivative at t equal 8, 54. We've got our slope, we've got our point, now we've got the equation of that line. And the next thing we want to do with that is we want to use the equation of that line to estimate the value of the function p at a given location. So we're just going to show, I'm going to demonstrate that if we plug in 8.5 into FL of x, we should get 323, which is an estimate for P of 8.5. So use FL of x to estimate P of 8.5. FL of 8.5 is approximately equal to P of 8.5, which is, let me redo that. Let me start back at saying P of 8.5 is approximately equal to FL of 8.5, which is exactly equal to 54 times 8.5 minus 8 plus 296, which turns out to be 27 plus 296, which turns out to be 323 cents. So what we're saying is P of 8.5 is close to FL of 8.5, and FL of 8.5 is 323 cents. So an estimate for the price of 1 pound of butter halfway through 1998 is $3.23. So that was a specific example. What I'm going to do next is just kind of generalize this. So f is our function shown in blue here. The point of tangency has coordinates c, f of c, and we are going to find the equation of that tangent line, and we can use that, as you can see, to estimate the value of f, because if the point where we're estimating is close to the point of tangency, the difference between the line and the function is fairly small. So again, starting from the point slope equation of the line, y minus y1 is equal to m times x minus x1, then we can say FL, we're going to call this FL of x. Oops, wrong one. Let's back up here. We're going to call this FL of x. FL of x minus the point on the curve and the line f of c, the y-coordinate f of c, is equal to m, and m is just f prime of c, the derivative of f at c, times x minus c. And that's the equation of our line. We're going to solve for FL of x. FL of x is equal to f prime of c times x minus c plus f of c. Notice that c goes in there in several locations. It's the x-coordinate of the point of tangency. It's where we're evaluating the function at, and that's our y-point, our y-coordinate of the point of tangency. And f prime of c is the derivative at that point of tangency, which gives us our slope. So there's the general form for the linearization at a point of tangency. So just to make sure everybody's got this, let's do one more example here. Full-time employees. A cubic model for the number of 20 to 24-year-old full-time employees over a 6-year period is given by f of t. You can see it's a cubic function. Find a linear model for the number of full-time employees. Use the rate of change of f at t equals 7 and the number of full-time employees at t equals 7 to construct the linear model. Use linearization found in Part A to predict full-time employment for the next 2 years. So that would be t equals 8 and t equal 9. Okay, so here's what we've got. Here's our cubic function. And just to visualize this, all right, we've got this point right here at t equals 7, and we need to know the coordinates of that point. So 7 comma f of 7, and if you plug that in, you get f of 7 being approximately equal to 9,589. 9,589. And that's our point of tangency. And all I did there was I plugged that into the function f of t, and you can verify that. I did round off to the nearest whole dollar. F prime of 7, okay, you can find that derivative using the power rule. So I'm going to suggest you pause right now, you find that derivative, and then you evaluate that derivative at 7. That turns out to be approximately negative 32, and that would be in thousands of employees per year. So FL of x is going to be negative 32 times x minus 7 plus 9,589. So that's the equation of our tangent line. All right, now we want to find, in part B, we want to estimate the value of f of 8 and f of 9. FL of 8, so let's back up here. F of 8, the actual value of the function, is approximately equal to FL of 8, which turns out to be negative 32 times 8 minus 7 plus 9,589. So that turns out to be about 9,556. 9,556. And that's an estimate for the number of employees. Because the slope of the tangent line is negative, so if I sketch that tangent line in here, you can see that it's got a negative slope. Our prediction is that at 8 years, the number of employees has decreased from the number of employees in 7 years, or at 7 years. C, f of 9 is approximately equal to FL of 9, which is equal to negative 32 times 9 minus 7 plus 9,589, which is equal to 9,524 employees. Just dawned on me that I was copying down my answers from when I didn't round. So this is actually 9557 with the rounding, and this is 9525 with the rounding. All right. So here's the thing that we didn't talk about that we need to talk about. You'll notice in the graph of the function for how many thousands of employees that it stops at 7 in the picture. Let's look at that a little bit more. If you can draw the rest of that function, as you see here, you see that the function drops off precipitously after t equal 7. So one of the things you have to do when you're making these estimates is you have to think about how close these x values are to the point of tangency, because the farther away they get, the more off your estimates can be. And another thing you can think about is if the function is decreasing to the right, then your estimate's going to be too high. And if it's increasing to the right, so if we drew our function going like this, then your estimate's going to be too low. So that is how we use linearization to estimate values of functions. Literally, we find a point on a function, we evaluate the function there to get the y coordinate of that point. So we've got the two coordinates we need for our point of tangency. Sorry, I highlighted 8, but actually it would be right over here. Then we find the derivative of the function and we write the equation of the line, and then for x values close to our point of tangency, we estimate the value of the function using the line.